Hello everyone, this is Nimai Karmakar from Monash University. I am the director of Monash Microwave Antenna RFID and Sensor Laboratory, and we have been working in precision agriculture. We are developing chipless and chipped RFID. Our team is Mr. Shubhashish De and me from Monash University, and this work is in collaboration with MIT Auto IT Lab. Dr. Rahul Bhattacharya and Sanjay Sharma are our collaborators. Outline. Before I am going to talk about this sensor development, I am asking a question. Can you make low-cost UHF RFID sensor for salinity as well as the moisture content measurement? As you know, Australia is a dry continent. It is the driest continent in the world. Saving water for irrigation is a big impact for Australian continent. Now today I am going to talk about the background. I will give you the background about the RFID concept and also the precision agriculture, how we can use RFID technology in precision agriculture. Then I will talk about the theory and soil model formation, because as you know that the soil is a very complex composition, and when the salinity, sand, water are mixed together, it becomes very difficult to model this soil. That means getting it dielectric property at micro frequency is a challenging task. Next one, about the sensor design. There I will talk about the candidate sensor that we have developed using both chipless and chipped RFID concept. Then I will talk about the result, and I shall give the analysis of the result. Since we are working at UHF RFID band around 900 MHz, so I will be giving you some design optimization technique to make this UHF RFID chipped sensor for soil moisture and salinity measurement. Finally, I will conclude the talk. I hope that you will enjoy this presentation. Now, background and motivation. First question is, what is precision agriculture? Precision agriculture is a modern data communication technique that provides real-time information of nutrients, pesticides, irrigation water uses, that is mainly using the sensor nodes. Here is a very nice depiction on your left-hand side by www.shop.wifi.com. 3 sites has been monitored with this kind of sensor nodes, and that can be supervised by the owner as seen on the very top left hand side. On the other hand, we can see that the data can also be sent to the cloud computing for agronomists and other decision makers. However, this kind of technology is very expensive, and the motivation of chipless RFID comes from there. I have been showing here the figure 2, where all the chipped expensive sensor node can be replaced with fully printable chipless RFID sensors that can be made very cheaply, maybe within few cents, and a sink or hub collects all the data from the sensor that are connected to the plant on the soil, and that can be sent wirelessly to the farmhouse, and from there wireless LAN and cloud computing. So that is the main concept of both chipped and chipless RFID for precision agriculture. Now in this slide I am showing you the RFID technology. Firstly, the basic definition of RFID technology, and then I will be showing you the concept of RFID sensor that is being used for the precision agriculture. What is RFID? RFID stands for radio frequency identification. It is a wireless data transmission and reception system between a transducer or tag or contactless card and the RFID reader or a scanner. The RFID reader sends the energy for the tag and that is mainly for the passive tag, also some interrogation data, and then clock. In return, the tag sends the identification data, and that is the key formation of chipless RFID tag. The coupling element between the reader and tag is the antenna for the electric field coupling or far field coupling. Inductive coupling or proximity or near field coupling is done by the coil antennas, and also you can use some kind of capacitive electrode to have the near field coupling. What are the key features of RFID technology? It is a very flexible technology, it is very powerful technology compared to optical barcode and other kind of coding technique or tagging technique. It is non-line of sight reading, that is the most flexible option for the RFID technology that has been obtained. It is robust and secure, and it can be long range, and reading is very fast. There is no human intervention required for RFID reading. Now the hypothesis here, can we add a RF sensing element with the ultra high frequency RFID, which is the electric field coupling or far field coupling. Here I am showing one such tag with chip. And to make this low cost, we need to do some kind of maneuvering or new smart design, or we need to remove the microchip completely. The main goal is to use the sensor for silent measurement. Let us see how we can make this happen. The heart of the design is called electromagnetic, in short EM, transconductance or RF sensor. That also called electromagnetic transduction or electromagnetic or RF sensor. Here I am going to show you my concept about the chipless RFID technology that will reduce the cost of this sensor significantly. How we can reduce this one? We can use the fully printable chipless RFID tag sensor concept here. As you can see, there are independent sensing elements that can be also multi-parameter sensor in a single node. Here I am showing you the humidity and temperature in the single platform, and dedicated resonance circuits or frequency sequence circuit for the identification. So our hypothesis is we want to create multi-node single parameter device to incorporate different components, that means temperature and humidity sensor. Let us have a look. What is the definition of EM transduction? It is one kind of sensor. It receives the stimuli in physical parameters like temperature, pressure, humidity, pH level, impact, and it can transfer this stimuli in electromagnetic signals. As you can see here, that we are having some kind of modification. That is the resonant dimension. We are changing the resonant dimensions. That means resonant dimension. We also have work with the material properties of the material under test, and we are also doing some kind of RF coupling between the resonator and the nanostructure. Here I am showing you these two different elements, that is called electromagnetic bandgap structure or metamaterial, that is loaded with some kind of smart material to create the temperature and humidity sensor. What else we can offer? Our concept here for chipless RFID sensor is fully passive, no maintenance required, no alarm component, no intelligence here. That's why you can make it very low cost. It is printable, and then it is compatible with harsh environment. There is no silicon microchip here. It can work in a very low frequency, low temperature, and also very high temperature. And we are integrating the identification data with this sensing element. So that means our hypothesis is we can create multi-node single parameter device to incorporate different physical parameters. Here I am showing you some background of precision agriculture using our fully printable Chipless RFID sensor to measure the moisture content on the leaf. The motivation, therefore, here we are working on this soil salinity and moisture content measurement. They are both critical for crop productivity. Particularly salinity creates huge problem for the plant growth, and we are targeting this kind of technology that can identify or detect or measure in real time without any wire the salinity content as well as the moisture content. So let's see one by one. Here is the soil salinity and moisture content measurement that is critical for crop productivity. Osmosis of water into plant roots is very critical, so we need to control by soil salinity level. And highly saline soil, they creates huge problem in production of crops. Then the grasses or pastures and also the trees, they interfere with the nitrogen uptake. So knowledge of soil moisture profile are critical for efficient irrigation scheduling. That is very important for Australian agriculture or any agriculture in the world, because water is the precious resource. And then the cropping practices or patterns, and we can also have the sustainable land and water management. So what we are doing between Monash and MIT, we are developing some very low cost soil salinity and moisture content measurement sensor, and we are using UHF RFID sensor. So far I have given you the background of soil salinity measuring sensor for precision agriculture, our motivation, and the hypothesis that we developed for UHF RFID sensor in the collaboration between MIT and Monash University. In the next slide, I am going to show you the design procedure for those sensor development. So we start with some motivation, hypothesis. Next, we need to have the proper model of soil composition. So with a lot of chemicals, it has sodium chloride into it, it has water. So how do we model this composite soil for micro frequencies? And the main constitutive parameter that we want to extract from this model is the relative permittivity, or called the loss tangent, and also dielectric constant of the soil at micro frequency. And this itself creates huge new field of research in this area. Next one, once we have done this permittivity extraction at microwave and millimeter frequency, we will be using this constitutive parameter for CST simulation. CST is the design environment suite for 3D model of any microwave circuit. Then we will be having this candidate sensor at UHF or microwave frequency band. Here we are using a very simple structure, which is a λ/4, that means quarter wavelength monopole antenna backed by ground plane. Now get this return loss versus frequency plot, radiation pattern to understand how it will interact when it is baked into the soil. That is very important to understand the working principle of this sensor. Next, we immerse this sensor in moist soil first and get return loss versus frequency. So as you see, that first we have designed this sensor in CST in free space. Now we immerse this one into the soil where you want to get these properties of the soil in micro frequencies. Then using CST model, we get this return loss, that is nothing but the impedance variation with respect to frequency due to the moisture content as parameter. Next is we need to get the salinity measurement. So what we do, we fix a particular moisture content and then we calibrate the soil using our sensor, and next one we use the different types of salinity. That means we're adding more salt into this soil and then we're getting the parameter return loss versus frequency to understand how the impedance variation happens. Next one that we calibrate for experimentation. So first we test this sensor in free space and then we calibrate it, and then we immerse this probe into the soil under test and we do the experimental variation with respect to the CST results. Next, the outcome is that the antenna has a fundamental mode and it has also the higher order modes. So we saw that the fundamental mode is less sensitive when it is baked into the soil under test. So what we are doing here, we are working on the second order harmonics. So we are having the second order harmonic frequency and optimize the sensor in second order harmonic frequency to get the sensor working at the UHF band. Then add the UHF RFID chipset with the sensor for our low-cost chipped RFID sensor, or we can use the concept that we have just discussed before, a fully printable chipless concept. And finally, we develop the prototype for the chipless RFID sensor and we stop and the mission is accomplished. In the last slide, we give you the design procedure. Now, in this slide, we will discuss about the soil model formation using Dobson's dielectric mixing model of seawater and sandy soil. What Dobson did, he did a very interesting exercise that gives you the dielectric constant, that means the epsilon r, real and imaginary part, the constituent parameter or permittivity of this soil from 1.4 to 1.8 gigahertz with a volumetric moisture content symbolized by m sub v. Here these are the two equations and I am not going in that details, but these two equations are used in our case, and also we can calculate the loss tangent by using these two equations. That means equation number 1 and 2. Equation number 1 is the real part of this relative permittivity and the other one is the imaginary part of the relative permittivity. Now our hypothesis is that Dobson's dielectric mixing model that will be used to calculate the permittivity of sand and seawater mixture. Why are we doing this one? Because we want to use this epsilon r values and tan delta values in our CST model for the soil under test content and different salinity and the real and imaginary dielectric constant. Next, the table is very interesting to observe that you can see with the moisture content, both real and imaginary part of the dielectric constant is increasing substantially, and likewise the loss tangent. Whereas in table 2, you can see a similar kind of fashion of salinity from 0 to 100. Here we are also seeing the real and imaginary dielectric constant is changing too, at the same time the loss tangent. So at 0 salinity, the real dielectric constant is 5.42, whereas 100 it gives 4.76. On the other hand, the imaginary part in table 2, it is 0.2 to 2.21. So this variation is less sensitive compared to the moisture content, and these two important phenomena will be used in our design that we are doing in CST Microfluidic Studio. So our candidate sensor element is a quarter wavelength monopole with back reflector, and this back reflector is also grounded with SMA connector outer jacket. Here I am showing you the simple model of our sensor. Here the lambda over 2 monopole is the black post shown here. The circular ground plane is the back reflector, and the SMA connector, the inner conductor, is connected with the lambda over 4 monopole. The outer conductor of the SMA is connected with the circular ground plane. The ground plane can be also other shape like rectangular, etc. Here the CST rendering with the dimensions are shown. The sensor length is 80.5 millimeters, and radius of this ground reflector is 19.05, and that operates at 1.11 gigahertz as free space. It is very important to conceptualize that in free space we are designing this probe at 1.1 gigahertz, but in the soil content it will be different, and that I am going to show you in a later space. However, here is the free space return loss versus frequency plot. We are seeing that close to 20 dB return loss is obtained at the resonant frequency, and this is the 3D radiation pattern of such a monopole with back reflector. And our hypothesis is that we want to actually design that at QHF band maybe around 2.96 megahertz while inserting into the dry soil. Let's see what is being here. In the first, when we put this probe into the soil container as shown in this figure, we are measuring basically S1 versus frequency. S1 is the reflection coefficient in dB, or return loss in that is the reflection coefficient dB here. So you can see that with dry soil that has a resonant frequency, this is from the red curve here, around 0.926 megahertz, and the return loss is very good, around 37 dB. So as the moisture content increases, the value is written in terms of V, MV, 0.1 to 0.4. We are seeing that the frequency is substantially shifting towards lower frequency from 926 megahertz to around 650 megahertz. And that can also be reflected in table 2 and table 1. We saw that with the moisture content, the dielectric constant changes significantly, whereas with salinity, the change is not that sharp or that broad. Here, now we are changing the salinity as a particular moisture content M sub V 0.1, and you can see the change is very minimum in other direction, whereas we can get around 38 dB of return loss as 0.83 order of frequencies, 0.83 gigahertz of frequency at MV equal to 0.1, and if you increase the salinity from 0 to 100, you can see there is some gradual change, but the saturation happens. So what you can see from this exercise, as the moisture content increases, resonant frequency shifts towards lower values drastically, whereas for a particular moisture content, if we increase the salinity from 0 to 100, the frequency shift is not that significant, and that also can be synchronized with the result in table 2 and table 1, that with the salinity the dielectric properties are not changing drastically, loss size is changing, and we are seeing the broadening of the Q factor and the saturation of the return loss point. We are moving from low salinity to high salinity. So that means the conclusion you can say that as the salinity level increases, the amplitude of the return loss keeps reducing with a saturation at a certain level. So if you look at 80 and 100 salinity, the saturation is happening and frequency shift is minimum. Now we also validated the simulation that we have done in our previous slide with this kind of very expensive setup. That is the Agilent, now it's called Keysight Precision Performance Network Analyzer, which can measure the signal up to 67 GHz, and that is available in my lab. We have done a single port S11 error correction calibration, and first, at the beginning of the experiment, we take a soil moisture content of 10 to the power minus 4 mil. That means that many part per 1000, and salinity level 0.055 gallon per liter. So we added that much salt there. So you can see the photograph here. The rectangular box, plastic box, contain this sandy soil, and first we have used zero moisture and zero salinity level. And how we can ensure that? By using a commercial hydroprobe sensor. We make sure that the first prototype that we are going to immerse into the sandy soil that has no moisture and no salinity. Next, we add this salinity as well as the moisture. First, what we did, we actually add the water, and you can see here 35 milliliter every step of experiment. We add the 35 millimeter of water, and then we give 20 minutes to settle the water mixed with the dry soil, and that is continued after 20 minutes, and then do experiment. Again you add another 35 ml of water and give 20 minutes to settle the mixing in the soil. That way we have got this lengthy experiment, and the result is shown in figure 9. As you can see in the figure, when the dry soil, that frequency resonance is 0.9 almost, that gigahertz, and with the increase of the water content and moisture content, the variation goes lower frequency from 0.9 to 0.5 gigahertz. So it is an exorbitant frequency shift, and that tells us that with the water, the dielectric constant is increasing significantly. That means the effective length of the probe is reducing significantly, and that's why we are getting very low frequency resonance. And one interesting observation is that the return loss, that is the impedance value, doesn't change much. The deflection profile remains almost in 16 dB of return loss. So that is very interesting exercise and understanding, and this science can be verified with the understanding of Dobson's calculation for soil formation in terms of epsilon r, both the real and imaginary part. Next, we can see the salinity. So there is no salinity to ensure with this probe. Next, we add some salinity slowly, say 4 gram of salinity and then 8 gram of sodium chloride in the salt, 12 gram. And what we are observing, the first resonance frequency became less prominent. But at the second resonance frequency, we can have noticeable change in the return loss performance and impedance performance. That's why we now concentrate more on the second harmonics than the first harmonic. So here, one by one, we can explain the finding. First, the response of 35 milliliter water content at no salinity as a first harmonic. It's quite sharp harmonic at 0.7 gigahertz, and that is quite natural because the water increases the dielectric constant, and that's why we are having from the previous 0.9 gigahertz to 0.7 gigahertz now resonant frequency. But when you add the salt, the first resonant frequency is almost disappearing. It can be seen up to 4 dB of return loss, but if not that prominent, that gives a measurable quantity. So that's why we are now shifting our interest from the first harmonic of 0.7 gigahertz to the second harmonic at 1.28 gigahertz. and the return loss depth is quite noticeable. That is a measurable quantity. Next, as we add the salinity, so I was saying that the frequency is shifting slightly towards upper frequency, but it is more on the Q factor and the amplitude of the return loss. So that two parameters can be used as the measurable quantity. Finally, the amplitude of the return loss getting saturated, and then we have to do another addition of water and do the test again. So as per experimental workflow, at this saturation point, moisture content is further verified by adding water. Now let's have a look at this measured result for different water contained and then the addition of salt. Here, very interesting curve here. You can see figure number B, adding this 70 milliliter water and changing the salt. We are seeing this frequency is shifting upward as the return also reducing, and then get some saturation. And then we add this 105 milliliter water, then we are getting another kind of stimuli that is noticeable. When we add this more salt, still you can get some noticeable parameter changes, then get saturation. And then we add more water, then we can add more salt, get more saturation. So this kind of a step-by-step procedure can be implemented to get the saline or salinity measurement in the water, in this file. So interestingly, what you can see, with adding water, return loss amplitude again increases. We know that. And then with salinity, we are getting Q factor to reduce again, we get saturation. And then we again add the water, then we are getting better kind of return loss. And then we again add the salt. So that way we can have a very good understanding the limit of saline content. So here we are working with two parameters, one is the moisture content and another is the salinity content. So this is the important finding that we have discussed. Now what you can summarize the finding. At no soil salinity that we tested in the probe, sensor exhibit frequency shift due to the moisture content variation, because with the moisture content the dielectric constant changes significantly and that frequency shifts of the organ. Next, we fix the soil moisture variation, and now at salinity we are increasing. So moisture variation does not enforce the frequency shift anymore, but salinity does. So we fix this moisture content at a particular level. So instead it fixed the resonant frequency at the second harmonic at around 12.54 GHz irrespective of the moisture content, because we are observing that when this salt is added, the first resonance is almost disappeared. Now Q factor could be one parameter of interest, because using the Q factor we can also get the salinity measurement. And then the hypothesis that we are hitting here, because we have to do ultra high frequency RFID band from 860 to 960 megahertz. So we can see that to achieve more robust and optimized sensor design that operate at the center frequency of this UHF RFID band, we need to tune or tweak our sensor further so that it will be in that frequency. So what we have observed from the previous experiment, that we have obtained some understanding that what should be the length of the sensor that bring us the center operating frequency within the UHF RFID frequency. And let us see how we can do it. So now we are optimizing this one. So as you can see that dry soil, that 1.1 gigahertz that we have tested in the second harmonics. Now we are shifting slowly towards 900 megahertz, and moisture content creates huge kind of impact. So if you look at the black curve for moisture content MP equal to 0.1 with 0 salinity, we can shift this frequency to 900 megahertz. That is our final design goal. So what you can see that from fabricated prototype, first harmonic was given at 926 megahertz. Then this response was shifted around 700 to 750 megahertz at 35 millimeter water level addition. So that is our initial moisture content. Second harmonic operates at 1.25 gigahertz, will become the resonance point for all salinity level. Third one, to operate this newly optimized sensor of 905 megahertz, even at saline soil condition, its second harmonic needs to be tuned at this band, that is around 900 megahertz band for initial moisture content of 0.1, and that we obtained from the simulation. Now what happened? Here the probe length increases quite significantly from 80 centimeter to 390 millimeter, 13.1 centimeter. So here is the result for particular moisture content and variation of salinity. The signal is within the band of 860 and 960 megahertz, and as usual that experiment shows that Q factor is reducing and getting saturated. So experimental analysis leads towards designing a sensor which operates entirely within the 3-chip RFID band. So finally, the conclusion that focused on experimental analysis and design optimization for very low cost soil moisture and salinity sensor, and soil simulation is very important to get this theoretical dielectric function, and that can be used as the input data for the CST microwave design. Then we design the sensor, and we have done both simulated and experimental verification. Fabrication is done, experimental is done, and the frequency shifting mechanism also is done for optimum performance. And from this obtained experimental analysis, we can design the optimized and robust sensor at 2-chip RFID. And the main final outcome will be when we add the chipset that will match with the 50 ohm input impedance of this probe, then we will have the complete chipped RFID moisture sensor with a very low cost solution. And we acknowledge the research from the Discovery and Interest projects by Australian Research Council, and we have recently published a few books in Chipless RFID sensors and Chipless RFID reader signal processing. If you are interested to purchase those books or consult those books,